everyone. I'm Wan Lee. Today's topic is distribution of sample proportion. It will be a good practice to check how much you understand my lecture so far, I think. Okay, let's see. Distribution of sample proportion. We often encounter data in terms of percentages data, proportions left to values such as support rate, pass rate, defect rate, market share, and so on, percent. You know what I mean. For example, support rate is the proportion of people who support someone out of total. Okay, the defect rate is the proportion of defective products among all products, right? It, everybody knows this kind of concept, I think. Let's examine a population that follow Bernoulli trial. Bernoulli trial, access Bernoulli trial. What that mean? Two outcomes. There are only two outcomes. One is success, the other is failure. If success, then X takes 1. If failure, X takes 0. Okay? Probability of X equal to 1, then means probability of success. And that is success rate. Let's denote it small p, success rate. Okay? This is a Bernoulli distribution. Suppose we obtain a sample of n from this population. From this population, we take sample size n, x up to n. Okay? Then x1 to xn identically, independently distributed Bernoulli with parameter p. P is what? We do not know the population success rate because we do not know all the data of a population. So it is unknown value. Parameter, P is parameter. And we already know that expected value of X is what? P. And variance of X, sigma square, is P times 1 minus P. We already studied this too. So you can remind all of them from previous lectures. Okay. In other words, we obtain a sample x1 up to xn from a population that follows a Bernoulli distribution where xi, because this is IID, these are IID, so xi is 1 if success, xi takes 0 if failure, I from 1 to up to n, right? Identically. Xi, probability of xi equal to 1 is small p, success rate. Now, we sum of these samples, say x1, x2, xn. x1 takes 1 over 0, x2 takes 1 over 0, xn takes 1 over 0. So sum of these x's, let it be x, capital X, another variable x. You can say this is u, something like that, in order to distinguish from random variable x. Okay. Either way, you may understand when even I write down x. Okay. Number of success among n samples. When each xi takes 1, then will be add up. That's why this one, x, is the number of successes among the n samples. When dividing x by n, like this, that is what? Success, number of success out of n. So it's going to be proportion, right? Then x is sum of xi's divided by n. So this is a proportion. Let's call it p hat. P hat. It's the success rate obtained from the sample, also representing the mean of sample. This is what? X bar, right? So p hat is like this, defined like this, then it is equal to the mean of samples, x bar, sample mean. So now n is sufficiently large, then by the central limit theorem, p hat, because p hat is mean in this specific case, p hat has approximately the normal distribution like this, with mean p, variance, population variance divided by n over n, right? So p hat may follow normal distribution by central limit theorem. In fact, population only has a meaning when the sample size n is sufficiently large, right? Sample size n is small, like 10, then in that case, sample size 10 case, the population does not have any meaning because it changes by 10% for each sample value. Okay? How about that? If you understand easily, accept today's lecture easily, many things has been accumulated in your mind, I think. So you are ready to study estimation next chapter. Okay, thank you. Bye.